Here we go. Nice to meet all of you guys. Today we will discuss the things called libraries for I/O operations, such as libuv, dart.io, and libevents. First of all, let me introduce myself. My name is Kirill, and I am front-end developer in the Live Editor team. I became to the Dart from the TypeScript, so I have some experience with the different ways to use I/O operations. And the last thing about me is that I have an unhealthy passion for digging up the source code of tools that I use. What we're gonna discuss today. First will be awesome library that called libuv. I tell you about what it is, where we use it, and how it works under the hood. Then I return to our cozy Dart environment, and we will try to find what helps Dart developers use I/O operations. At the end, we will have small dive to the browser's input-output. So buckle up, we start. What is the libuv? Actually, it is the acronym for Unicorn Velociraptor Library. First time I was like, wait, what? For God's sake, I have a definition of it from official site. libuv is a multi-platform support library with a focus on asynchronous I/O. It was primarily developed for use by Node.js, but it also used by luv, Julia, PyUv, and other stuff. Okay, now that sounds more clear. To get better what it is all about, let's have a look to the abstract model of Node.js architecture. At the upper right level, there is an application code with all business logic. The next layer contains two-part Node.js bindings and C or C++ add-ons. We are not going to discuss add-ons at length. I'll just mention that they include such libraries as OpenSSL, well-known general purpose cryptography library, and zlib, lossless data compression library. We are going to emphasize Node.js bindings. This is a middle layer between Node.js and API of C or C++ libraries, including C arrays, a C library for asynchronous DNS requests, which is used for some DNS requests in Node.js, and the HTTP parser, a lightweight HTTP request and response parser library. And of course, now we'll move to the core of Node.js, in particular to the engine V8 and libuv. Probably most of you know that V8 is the Google open source high performance JavaScript engine, written in C++. It is also used in Google Chrome browser and others. Node.js controls V8 via V8 C++ API. A majority of operations that language JavaScript can execute are run by this engine, as long as it's not about synchronous operations. In this case comes libuv. This library provides mechanisms to handle file system, DNS, network, child processes, pipes, signal handling, polling, and streaming. It also includes a thread pool, also known as worker pool, for offloading work for some things that cannot be done asynchronously at the OS level. In the one thread per client systems like Apache, each pending client is assigned to its own thread. If thread handles one client blocks, the operating system will interrupt it and give another client a turn. The operating system thus ensures that clients that require a small amount of work are not penalized by clients that require more work. As Node.js async logic was inspired by Nginx, it handles many clients with a few threads. If a thread blocks handling one client's request, pending client request may not get a turn until the thread finished its callback or task. So the event loop notices each new client connection and orchestrates the generation of the response. All incoming requests and outgoing responses pass through the event loop. That means that if the event loop spans too long to any point, all current and new clients will not get a turn. In the description of event loops work in Node.js, it said that all of the tasks are run synchronously in queue, except the IO operations that are run asynchronously. This events handling is work of libuv, as you see on the right side of slide. To get better look how all of this stuff works, I invite you to the fascinating world of source code. So those of you who worked with the Node.js may know that file system interactive has built-in library called fs. For my investigate, I choose copy file method. So here we go. Obviously, method implementation starts with basic arguments handling and validations. For example, you can see check for callback that should be a function. Meet a hard and cruel work without static typing in program language. Then we create a fast rec callback. It's some kind of universal wrapper for callbacks in async file system methods. So you can think about it like as an entity that stores asynchronous metadata of method, for example, callback. At the end of it, we send our data to the Node.js binding layer. You might remember it from slide with a scheme of Node.js. Here it is, that layer between Node and libuv. Then binding just maps us to the C++ layer, to the method that matches with the one we called. Method implementation by itself starts with a bunch of input properties checks like check GE. There is greater or equal and check not null. Then we have handling of rec wrap callback. If it exists, we know is it a method synchronous or asynchronous. After it goes some C++ magic, but we shall not delve into it. Here we are only interested in the method uvfs copy file from libuv library that will call from inside. And we hop down again. First parameter in the instance of event loop, despite the fact that parameter is not required in current method, for uniformity, it passes to each of method. So second parameter is the entity called request. Actually, IO operations, sockets connections, stream operation, and a bunch of other stuff relies on these entities. So let's say that it's some kind of primitive base of asynchronous operation. Two next parameters is the source and destination paths for our copy function. Next one is the mapping of flags that passed to the method. And the last one is the uv callback function. If it's a synchronous call, it would have null value. Next, it goes init copy file macros call. The thing is that requests inside libuv are really abstract, and these macros apply additional features to them. In the next line, we've got some flags checkups, such checkups at the node layer, but as libuv is used in not only there, they would be helpful as well. Next, we have fs capture path. Pulling of this function is for basically taking the path from the passed in and make copy of it. Because if we are doing an asynchronous operation, there is a chance that memory could be fried by the time an operation completes. If that happens, you're probably going to the hard crash. And then finally, we add the flag to the request. At the end, we call post. The post is another macro that is going to send our work off to the thread pool. It's okay if now you look like him, but be brave, it's not the end. Now let's see what happens inside macros post. And the first thing we should notice is check up for the callback function that lets the macros identify if operation is asynchronous or not. If it's asynchronous, that goes to the method that register a request in the event loop. After that, the process will keep alive till the request is processed. Then the method uv work submit will be called. It loads off the request from the thread pool. In the call of that method, you see uvfs work. As a matter of fact, it is a big switch case that decides what type of operation you want to run and runs the code section specific for this operation. UVFS done contains the code that is run while request loads off and take us back to the JavaScript layer, Node.js in our case. In case the synchronous operations execution will directly runs UVFS work and then returns result. No event loop, no asynchronous magic, just run it. Big thing about all of this that cross-platform of the library is reached by wrappers of the operating system APIs. On the next slides, you will see the implementations of Windows, just because they're a little bit shorter. Don't worry, versions for Mac and Unix systems not much different. There is a Windows implementation of fs copy file, as I said. It calls by uvfs work from previous slide. So at this layer, we have some operating system specific flag validation. Obviously, some flag stuff that we have on the Mac OS not supported at Windows and vice versa. And then we go to the copy file W call of the Windows API that handle copy file for you. All code below you see is just some kind of fix for busy state at Windows. So in our case, it doesn't matter. Now that's it. You have a top level picture of how libuv is working in the case with Node.js. Honestly, the idea for this talk came to me at the first months of my work in Wrike. While studying Dart, I noticed that I understood the main principles of how language compiled to JS works, since before that I have been working with TypeScript for a long time. However, a front-end language that also has its own virtual machine was new to me. Also, this part was most mysterious for me, and perhaps the most mysterious was the Dart.io library. Let's go through how this thing will make a copy of file. To begin with, in Dart.io, copying a file is runs through the copy method of the file class, as you know, and it looks like this. Return, then return, okay. Looks like small callback hell for me. And the main point of what happens here is in the transfer of copying data to the dispatcher. IO service is the large store of sequence numbers for operations, and it has dispatch method interface to send these numbers. We need number for file copy. The dispatch with namespace method in turn forwards the current namespace to the dispatch implementation inside IO service. As you may have noticed, the base implementation of IO service has not contained the implementation of the dispatch method. The fact is that functionality is added for this service using patch decorators further. Here we see one of these patches. This is where the free port is obtained from the thread pool analog. A completer is added to the message bus, which is responsible for completing the work after the task completes. Next, through the send port of Dart isolates, our request reaches the C++ layer. Actually, dispatcher bus is quite simple. It's received requests from the Dart isolate port, convert arguments, and send them to the C++ methods. Pretty similar to Node.js binding layer in case with libuv. And now we all at the C++ layer. Here, the first thing is to parse the received request and its arguments. Next, we use IO service request list, some kind of macro, to convert the operation number back for copy. After all of it, we run assert macros. It calls method that we get from IO service request list by ID and passes arguments to it. This brings us to the file copy function with the following implementation. First, it checks the existence of file, and then it used copy file xw function, which is the extended version of copy file w that used in libuv, as you may know. It can receive callback and can be cancelled. But however, as you can see, it is not used here, so it's kind of weird choice as for me for this stuff. Actually, it would be fair to ask, okay, Kirill, that's all fascinating, but what about browsers? How do asynchronous IO operations work here? This is a timely question because, as we discussed, libuv is used in the JavaScript world, but only in Node.js. The Dart IO implementation is only applicable to servers because the client code will be compiled to JavaScript, as you know. So the answer to this question is pretty short. The browsers have, based on Chromium and the Firefox, uses the library called libevent. It should be noted that it also used by products such as Memcached, Tmax, Transmission, PG Bouncer, and etc. Like most other C libraries, libevent has a mind-blowing official site design, as you see. This library, unlike libuv that used synchronous call from thread pool, used buffered IO for file system operations. I can say something about reasons of choosing this library by popular browsers, but who knows? I bet that this approach better fitted for client side. This is where my story is end. I hope you are interested as I was when I was digging all this up.